Welcome to Complexity Made Simple. My name is Paul Allen. I'm the subject of today's video newsletter. Well, I've had a request from a viewer who'd like me to cover response surface methodology. So it's a DOE technique. It's often known as RSM, response surface methodology. RSM, and it is a subject that it's still referred to today, it's still used today, but this is quite an old-fashioned technique, and we're going to talk about why it was developed when it was developed, and essentially how it was used back in the 1950s, 1960s especially, and why actually a lot of the methodology today isn't really needed. And that's partly because today we have computers to do what RSM was designed to do. Okay, so let's talk about what a response surface is in your DOE. Normally when we think about understanding a process, let's say we're gonna understand what time does to a process. We're going to go from 10 seconds up to 100 seconds. We're going to see what the effect is on the, let's say it's the strength of a molded part, and this is cooling time, it could be. So what we'd of course do is we would test in different places and we would get this response. Now this diagram is two-dimensional. It's just a flat picture, and of course it's very easy to understand. You know, I could almost by eye say, well, if I set the result to 50, you could almost read that off just by using the diagram. It's very easy to understand. You don't really need any mathematics. You know, you're going to have some simple y equals mx plus c equation that represents that straight line. It's very simple to understand. But even so, the diagram is very useful. The diagram is very useful. And the response surface is essentially the same thing, except it's not two-dimensional, it's three-dimensional. Because if you were to understand now, if I were to test time in this direction, there's the response going in that direction, time in that direction, but we've also got temperature in this direction. So imagine now this line starts to go backwards. So instead of it being a flat line, it's now a plane. It's going to look like this. So if you imagine this is the straight line, obviously I'm looking straight at it, but if I just tilt my head, I can now see this effect going in this direction, which is caused by the temperature. Now this plane is known as a response surface, and it's very difficult to draw these things in 3 dimensions. I can't really do it. I'm just going to kind of draw something very simple. You would get a 3-dimensional response surface, and the reason why these response surfaces are needed, of course, is when we start talking in 2 dimensions or 3 dimensions, or indeed if these surfaces are twisted in shape, so they are curves in shape and things like that, it becomes almost impossible to understand what the hell's going on. And as I said earlier, these were invented. George Box is credited with inventing response surface methodology, and he invented it in the 1950s and the 1960s in the chemical industry. Why did he do it? He didn't have a computer to understand his process, so he needed some simple pictures to help him. So he invented this technique called a response surface methodology. Now I'm going to show you a computer generated one of these. This diagram here, look, this is an interaction plot, exactly what you're seeing for time and temperature here. It's an interaction plot, and you can see that the surface is twisted in nature. It's not a straight plane like I showed you with that white sheet of paper. Just it's twisted, and it's showing you an interaction plot. And if I show you the two-dimensional interaction plot, so here's the two-dimensional interaction plot, and if I indicate, look, this line on the interaction plot is the front edge of this response surface. So this line here in red represents this line here in red. If I go back to my interaction plot, the two-dimensional version, this straight line that's now been highlighted in black is this line on the response surface, also being highlighted in black. And of course you can see that we're looking at the three-dimensional version of that, and those two lines are opposing one another, so the plane twists in space, and that's known as a surface plot. So that three-dimensional thing that you're looking at there, the idea of response surface methodology, is known as a surface plot. So these pictures were drawn to be able to understand where the top of the curve was. So why did Box do this? Number one, he wanted to understand how to optimize the process model. In other words, he wanted to know where the peak of that curve would sit. And just by looking at the maths, it wasn't obvious where the peak might be, especially with interactions in a model. And this was very difficult to do in your head. It was very difficult to do mathematically. But if you look at the diagram and you want to go to the highest point on this surface, for example, and often curves were part of the problem in George Box's processes. So this curved shape, Box wants to know how to get to the peak of that curved shape. And the best way to do it is to draw the picture, and he can see where the settings would be. So if I follow the scales down this diagram, for example, it would tell me to set one variable to this point, and it would tell me to set one variable to this point. And he can see with no computer how to optimize his process. So that's reason one why we draw these things. Reason two, though, is to find a sweet spot for multiple responses. So again, today the computer does this. So one of the reasons why we don't need this much today, the computer will find an optimized spot today. So I can just say to the computer, please take me to the highest place in this model, and it will do that. Also, the computer, if you have Minitab, for example, Minitab will do this. If you ask it to hit two targets at the same time, it'll tell you where the sweet spot is, or it'll tell you the sweet spot doesn't exist. Well, the technique for hitting the sweet spot was to use a response surface. Now, it wasn't to use the three-dimensional diagram that we've just looked at. They were going to look at something called a contour plot. So the contour plot, let's imagine here we're playing with this this molding process again, time and temperature. We want to get the strength correct, but we'd also like to get the weight correct. So we want to make the molding as light as possible. We'd like to make the molding as strong as possible. So we would draw one of these diagrams which would show us the weight. We would also draw a diagram then that would show us the strength. So we would draw two diagrams. The diagram we would use, though, is known as a contour plot. A contour plot. Now the contour plot is flat and it's got contour lines on it, just like a map. So you would draw a contour plot. You would have time and temperature on this contour plot. This would be the strength contour plot. You would have time and temperature on this contour map. So let's draw something slightly different so it makes a bit more sense. So I'm going to draw something that looks like this time. Okay, so this contour plot wouldn't be showing strength, this would be showing the weight. And we would have a target strength, which could be in this region here. So the centre of that region would be the absolute nominal that we're trying to hit. The size of the box might be the tolerances that we're able to be in. And then for the weight, same thing, we might have a target and we might have a tolerance. And what they would do is they'd pick this up and they'd put them over the top and they would look for the point where these two regions overlap one another. So maybe if I impose the weight box on here and there is the point where they overlap, that's the sweet spot where I can get closest to the strength and closest to the weight. And so they used to draw these on an acetate. They would do it by hand. They would draw a contour plot. You can see the contour plot here. The computer is drawing the contour plot for me today. So here's the contour plot of this three-dimensional space. You can see the contour lines are there to represent the shape of the hillside, just like looking at an ordnance survey map. What we do is we lay those two contour plots over the top of one another. We look for the sweet spot region, and that is the point where we can hit both targets at the same time. Now this technique and this technique today, we don't need them. The computer does the work for us. So the computer will tell me where the peak of this curve is. So this diagram here, look, although I can see it on the surface plot and I can see the hillside and the top of the hillside and where the two settings would be, actually I can also just go to the software and say take me to the maximum, and it will do that. The same with this problem here of looking for the sweet spot. I can ask the optimizer to hit the two targets and it will tell me whether that's possible or not. So this technique in response service methodology, it isn't really needed anymore because today the software does the work. The one thing that I do use the response surface for is on the interaction plots. The interaction plots tell me where the flat spot is. Now software typically won't do this, but what I'm looking for, look, let me just show you, just get some space here. When you get curvature, I'm going to draw it just as a two-dimensional diagram for a second. Again, let's say that this is time. This is strength. Alright. Now, look, this region here, I can move time backwards and forwards. What happens to my response? Well, it moves almost imperceptibly. That is a region of robustness. So these areas of the flat spot, it doesn't always have to be the maximum or the minimum, by the way. In twisted planes, sometimes the flat spot is in the middle in terms of the highest response value and the lowest response value. The robust region is actually in the middle. But what we're looking for is when these surfaces go flat, they are regions of robustness. So I could set my time here, my tolerance could be nice and wide, and I would get an imperceivable effect here on my output of interest. However, look, if I take that same tolerance and I drop it here, and I'd set time there. Well, now look, if I allow time to move backwards and forwards, wow, the same tolerance for time, the same tolerance for time. Here it has no effect, here it has a massive effect. Now the software can't do this, but the response surfaces can show you when the side of the response starts to go upwards and get steep, the incline gets very steep, that is a region of sensitivity. Keep away from it. Where the surface goes flat, that is a region of robustness. Use that, set your tolerances around that, set your settings around that if you can. Okay, so that is what you would use response surface methodology for today. You wouldn't use it for these two things because the software will do the work. Now, one final thing, response surface methodology has become associated with particular types of DOEs. So often in Minitab, for instance, the central composite. So the central composite design. Central composite, often also called the CCD, central composite design, can only be found on Minitab on the response surface menu. So this DOE was generated to generate these diagrams. It's effectively there to spot curvature. The central composite design is there to see curvature. So if you think you have curvature in your responses, forget the response surface methodology necessarily. You need the CCD just to capture the curvature in your models. Then you can find flat spots by looking at the diagrams. You don't have to do this anymore because the software will find the optimized regions. But that's how we use response surface methodology. It was invented in the 1950s by a wonderful British mathematician called George Box. In his day, it was absolutely vital that he had these tools in order to optimize and understand complex systems. Today, we use software to do the same thing, but go find robust areas. That's the use of response surface methodology today. And if you use response surfaces, if you find regions of robustness like this, your tolerances will be wider, you'll please the customer in a much cheaper and easy to achieve way, and basically you'll make more money. Response surface methodology.